something? That'd be Nikish.
Yeah, I know. For a second I thought we had to, but it's just like, looking at my suit, I was like, you're pretty loyal. And shit, good enough. That's what the teacher and my dad's from Masters now. Fashion. Quick design.
YOLO just split around. Might be right here. There we go. Chen, you want to first?
I think so.
Yeah.
If we go in order.
There we go.
I'm not transferring it.
Are you first?
Group 1. Or group 1. I think so.
It was
No one's mentioned.
case studies.
Yeah, makes sense.
No, I'm group 3, man. We'd rather get it out of the way. Yeah, we'd rather get it out of the way. I'm that sort of guy. I'd rather do it right at the start, man. Just get it done.
Get out.
I hate sitting around waiting.
Building up the tension.
Yeah.
Oh, really? Let me my two. No, I'll change that one.
Just put your group number.
No.
Change it to a text file.
Just YOLO.
I want to play a game.
If you're not transferring anything, don't worry about it. Yeah, you can't do it. Not lucky, man.
I'll just select everyone else's presentation, rename. Just like,
YOLO.
oh, thanks, man. Yeah, I was missing that this morning. Thanks. Yeah, thank you. I hope so. Yeah. I'm pretty nervous.
lost that USB.
Oh, no. There's someone else's sessions open in the Chrome there? Just be, they've got theirs like online?
OneDrive, right?
Yeah, I think it's
Yeah.
Gotta check it works.
Queensland next week?
Sorry?
Queensland? Which set of origin?
Not really. No, I'm done. I'm presenting first. There's one on OneDrive.
Oh, I see it.
Yeah.
So where do we?
That's there.
Here?
Yep. It's all right. Stress. Right. We're group one.
Okay, so we are going to be boring and just go through one.
Okay. Good morning, everyone. My name is Cameron Stewart, and I'm representing Group 1, which is presenting the sliding hinge joint for steel moment-resisting frames. Group 1's myself, Luke Shaw, and Yi Shen in the audience there. First of all, the aim of the sliding hinge joint. The aim of the joint is to provide a joint that has two different types of behaviors depending on the seismic demand on the structure. You can see here in the AADRS diagram, up to the design level earthquake, the structure is designed to behave rigidly. So that means for a service level event or wind loading and stuff like that, the structure remains rigid. Once we exceed the design level event, the joint's designed to behave flexibly, allowing the structure to displace without an increase in the moments and forces induced in the structure. So here's the joint. The dimensions that we show here are based on experimental experiments in the literature. That's where we got the section sizes from, the bolt numbers, the plates and stuff like that. So this view shows the assembly of the joint from below. We can see here we've got, this is the main area of the sliding hinge joint. That's where the magic happens. Removing the bottom cap and some of the bolts, you can see the slotted joints, the slotted holes, sorry. That allows for that rotation, and that's what gives the joint that capacity to rotate. Going back, these the bolts installed here are installed friction tight, so they're tensioned up to provide a clamping force on these plates here, and that's what creates the friction at the base of the joint, and that's what basically determines the rotational stiffness of the joint. So you can change the tension, number of bolts, the interface materials to vary the friction force that the joint needs to overcome to rotate. Moving a bit further, taking away the beam, you can see that the joint's quite simple. It's only 3 plates with elongated holes, excluding the other parts of the mechanism, other parts of the joint, which makes it quite cost effective because fabricating this as opposed to fabricating a normal moment resisting frame joint is pretty much the same amount of work, so it's favourable in that regard. This animation shows how the joint deforms and develops the hysteresis. Rotations primarily around the top flange plate here. As rotation occurs, we overcome the friction force that's being resisted in that bottom sandwich of plates, and that's what allows the hysteresis to develop in this form over here. You can see that we are developing some moment, and then we're sliding, so no degradation in strength, but just additional displacement, and then again where the second sliding occurs. These two surfaces may actually be much closer together. As the load's reversed, you can see that the behaviour is the same in the reverse direction as well. And you also note that we've got a rhombus-shaped hysteresis, which is typical of a friction slider dissipation mechanism. Okay, some advantages and disadvantages of the joints that we found in the research, that's noted in the research in preparation for this presentation. An advantage, which is one of the main aims of the joint, is to decouple the frame strength and stiffness, so the two things are independent. The next one here is the lower principal structural cost. So because the joint is rotating before that moment is developed, compared to a typical moment resisting frame, the section does not need to resist such high moments, so the sections can be reduced, and that cost saving can be passed on into the actual joint itself or other damage resisting technologies in the building. Another advantage of this joint over some other low damage technologies is the inelastic demand is confined to within the bolts. So some other technologies may have a fuse or something that's meant to yield and be replaced post-earthquake. In the case of this joint, that's the bolts, which are a relatively low unit cost item and a lot less difficult to replace than maybe a member or some other component. Another advantage of this joint, as opposed to in a normal moment-resisting frame, as I said before, the rotation is principally around the top flange. That means that the strains that are induced in the slab are minimal, as opposed to a moment-resisting frame. So they would have a lot more higher strains in the concrete, cracks in the concrete, damaging the slab, which obviously increases the cost of rectification works. Just on to some of the disadvantages. One of the disadvantages is highlighted in the literature is the residual drifts. As it's a sliding mechanism, the load may decrease when the building's drifted, and the friction will prevent the building from correcting itself. That's one of the issues there, but that's typical with friction sliding mechanisms. Another disadvantage is low and varied residual joint strength. So as the joint's deformed, the bolts have got moment, axial, and shear forces in them, and that deforms the bolts and results in a loss in tension within the bolts, which reduces the friction between the plates, and so the stiffness of the joint post design level event is not the same as it was in the seismic level event condition. Another disadvantage that was listed in the literature, and that's due to the limit of research, is that up to date, the design of this joint is only considered in a one-way moment-resisting frame. Okay, I just quickly want to touch on some modifications that have been proposed for the joint to try and counteract some of the shortcomings that I mentioned before. The first one being the self-centering variation, which is self-centering sliding hinge joint, which has a ring spring. So the ring spring is providing a force, restoring force. So as the buildings in the shakedown of the earthquake, as the earthquake's dissipating, that spring is supposed to return the joint back to its zero rotation position. And it does that, but it's found that the force that's required by the spring to do that is quite high, which means that the springs are quite high, the cost is high, and to an extent it's prohibitively expensive. Another modification that's been proposed is Belleville washers or springs. These are these deformed washers to sit in the to go in here on the in the bolts that get deformed. That's to try and maintain that axial force, to maintain that friction force, so the joint post design level event has a good level of rigidity and returns back to its initial condition post the earthquake. So it's been pointed out that the addition of these can actually increase the drift problem, can cause the building to drift out of position a bit more. So we've got our 6-minute limit. So in conclusion, recommendations. So based on our limited research that we did leading up to this presentation, we found that there were a number of questions regarding the joint. A few that I wasn't able to list due to the time limits we've got here. But we think that there needs to be a lot more investigation to really nail down some of those issues before it's implemented wider in moment-resisting frames. All right, thank you. Next.
All right, I'll just quickly rename my file because that's probably not the best name for a presentation. Has to presentation group 2. Oh God, I can't spell. Oh no, that's why I do engineering. Sorry, it's been about 5 years since I've used slideshow from beginning, and this means I get to click through it, doesn't it? Yeah, cool. Okay, so hello, I'm Michael, I'm representing Group 2, and I'll be looking at both research towards implementation and current implementations of the sliding hinge joint for moment-resisting steel frames. I will honestly just refer to it as SHJ from now on because, my God, it is a mouthful. So because the sliding hinge joint is actually pretty recent, it's only really come about in the last 10 years, there aren't too many applications in its wider use. As Cameron noted, there are a couple quirks they're still trying to work out. So there's really only 2 real-life implementations. So I'm actually going to look a bit at the research towards actually being able to implement this technology a bit before I get into the actual application, so I can stretch this out to 6 minutes and get a good mark for my group. So the first little thing I'm going to look at is the initial development of the sliding hinge joint. This is where the research was put into it to actually develop the design procedures for the sliding hinge joint. So this is done by a dude called Clifton in 2005, and this was part of his PhD thesis, so he probably wouldn't have been too much older than us when he got this out. This is going to be a very brief summary because the document related to this is over 100 pages long and I only just kind of skimmed it. So as part of Clifton's research into this, he performed 4 large-scale tests. You can see this very quality picture here that I was managed to source from his PhD scan here, where he mocked up 4 large-scale real-life tests to actually just kind of nut out the design procedure quirks and the things he really had to take into account as forming this. So this is just a picture of the large-scale test that was performed. You can see the slab, the other side of the hinge here, this is the instrumentation used in actually going through the analysis of the sliding hinge joint. So you can see actually the sliding hinge mechanism at the top and the bottom here. This is instrumentation used to record the data. You can see this is a stiffened column because you do usually want a stiff column when you are dealing with this kind of stuff. Yeah, so he also performs, so this is more pictures of the large-scale test setup. I was going to pull more pictures out, but I couldn't find any more. And this is just the loading regime that these large-scale tests were subjected to. So you can see, like, they just measured the moments and rotations over a time series as part of their analysis. There was also small-scale dynamic and static testing. Part of this where they had some like force rotations and applied over like a time scale just to really get the nitty-gritty details out on like individual bot performance. As part of making sure that this like thing that he was proposing, you know, wasn't going to kill people if it was implemented in real life. So these are the sequence of design actions that came about as a result of all of this research. Was proposed as part of his PhD. There's 14 steps in the basic design of a sliding hinge joint. So I guess this would be like the key bit of research towards the implementation of the sliding hinge joint, being actually able to design this stuff in real life. My inner bogan slips out for a minute there. The next little bit of research is the effect of the shim material. So as you also saw on Cam's slide, what the plate of material that actually forms the frictional surface, the primary like mechanism by way of energy dissipation through the surface, is called the shim. And in Clifton's initial research, like the first little instance of this technology, he used brass. But brass isn't always the most cost-effective of choices to use. It can be a bit expensive relative to other materials such as steel. So what was done by McRae and others is they tested out the shim material based on a real-life situation. This is a full-scale simulation of a sliding hinge joint in real life. And you can again see it all happening around here. So what they did is they used different shims in this little section here. They tested out brass, steel, and aluminium just to see, you know, which one would perform better. Because obviously, if steel works better, then that's absolutely fantastic. Or steel like works along the same lines of brass, because that means it's cheaper, has similar behaviour to like corrosive behaviour to the rest of your frame. Really, just works out really nicely. So they ran these tests. They got some test results out of here. This is just a closer view of the test configuration that was performed. So they got their test results out, and what they found is that the mild steel that they tested had behaviour that was congruent to brass. So the benefits of that towards the actual implementation of the research is that steel has its own intrinsic benefits. So like I mentioned, its cost is a lot cheaper than brass. It's a lot more available. It's easier to install. As well as having similar corrosive behaviour to its like surrounding parts. So like you've got your beam and your column, and if that's all steel, and if you have like a steel like shim in there, it's going to have like similar corrosive behaviour, which is really nice when you're actually like doing your corrosive analysis. Aluminium, whilst having a greater initial frictional resistance, over time as it slid, it actually lost that frictional resistance. So that was an issue with using aluminium, and why they decided to not go with aluminium for real life applications. The next little bit of and this is just a column hysteresis that was formed as a result of this. Moving on to the self-centering sliding hinge joint. So Cameron actually mentioned this a bit, so I'll fly through this. So you've already seen this picture. This is a ring spring that they throw in there just to help like realign the joints if it's subjected to some like external like force. So if these are sliding, you want to bring it back to like its initial state after you remove the load, because otherwise it's probably not going to perform as good if you do apply some new loading. So the testing for this was based on a real-life application of the technology. So this is actually a mock-up of Tapuni Village, which the Tapuni Village student accommodation buildings, which I will get to in a minute. So this is actually based on a real-life scenario, just to see if they can improve the behaviour of something that is equivalent to like this real-life application. Go faster.
Well, I don't know if it's
Oh, believe me. And these are just the common hysteresis that we're showing. Moving on to the actual real-life applications of this technology is the Bellagio apartment building. This is the first implementation of this sliding hinge joint in real life. They used 200 in the construction of this building of the one-way frame. This is the first thing. There's not too much documentation regarding to it, so I couldn't actually get any open plan views of this. However, but if we move on to the Tapuni Village, which is actually part of the Victoria University campus in Wellington, there are better. This is essentially like the textbook case study of the sliding hinge joint in real-life application. So this is a one-way moment-resisting steel frame, and you can actually see the sliding hinge joints in applications here. I do actually have a closer-up picture of this. You can see one here and here, one way that's halfway through installation. So this is more or less a casebook study. This is just the SHJ detailing regarding this. This is a textbook case study. There hasn't really been too much because they are still working out the nitty-gritty details of how to apply this in a wider range of scenarios. So Tapuni Village is a real-life application of it. These are the references that I used in constructing the actual report, which goes into far more detail. This is not the total content of the report, obviously because of time constraints. Hopefully I got under 6 minutes there. I hope that was satisfactory and I haven't popped that up.
Hey, I'm from Group 3 and we're doing our supplemental damping devices, and we also got Anton, Yu Yang and Leo, but I'm not sure which one of them are here. The main function of the damping devices is the dissipation of seismic energy. It's pretty obvious. It's also to reduce acceleration and displacement, unlike some of the other technologies which do one or the other. It can be used on new buildings or retrofitted to existing ones. It's usually placed at foundation level or in replacement of diagonal braces. They're easily removed and replaced. They can be combined with or substituted for base isolation systems. So especially with like some tall buildings where you can't do base isolation, these can act as a substitute. There's 3 broad categories I want to look at today, but the main aim of all 3 is to basically just convert earthquake energy into heat. So the first kind is a viscous damper, which is basically just movement of a fluid within a cylinder. So it's basically just a cylinder with a viscous fluid in it, with a piston with some holes in it. So when a force is applied, the viscous fluid can push through the piston and slow it down. So I got a quick video of how it works. If it loads. Oh, great. Okay. So you can see it's basically as it pushes, the fluid pushes through it and the piston moves. And there's a real life experiment coming up, which some of you might have seen. So you can see it makes a huge difference. It's literally just like the little toy truck is just going nuts. That's that. And the advantages of the viscous damper are that they obviously significantly decrease structural response, and they have better performance in reducing base shear than some of the other technologies that I'm going to look at. The disadvantages are that it's pretty expensive and it's sensitive to temperature. And the last one is that the resisting force depends on the velocity. So basically this is because if the peak structural response occurs early in an excitation, the velocity won't be high enough for the damper to actually work effectively, because as you guys know, damping is dependent upon velocity. The second type I'm looking at is friction dampers. This is literally just 2 bolted metal surfaces just rubbing together. So the friction between them is effectively what creates the damping. It's used in a wide variety of different types of structures: low damage steel, timber structures, resisting frames, and diagonal braces. And I got another quick video how it works. It's pretty cool. Yeah, so it's literally just a bunch of metal plates bolted together. So as like a lateral force is applied, these metal plates, the friction just causes the damping. Cool. The advantages are that it's reliable and insensitive to temperature as well. It's simple, foolproof construction. As you just saw, you could just bolt 2 metal plates together. For that reason, it's not expensive, and it doesn't require repair or replacement after an earthquake. The disadvantages are durability concerns. Obviously, you've got two bits of metal rubbing together, so over time that causes certain issues like just wear and tear and stuff like that. So for that reason, it's only recommended for dry internal use. But I'm pretty sure I read in the readings that in New Zealand they're trying to get it to work everywhere, so I don't know. And it's only used to prevent elastic deformation at the moment as well. The third type is the yielding damper. This is basically just a bit of steel acting as a diagonal brace, which is designed to yield and plastically deform if an earthquake was to occur. The main type is a buckling restraint brace, which is basically an encased steel core, and the case is there to prevent buckling. So I've got a picture of it here. So it's literally just this steel core could like replace a diagonal brace in a building, and it's encased, and basically if an earthquake hits, it's designed to yield. The advantages are that it can be put on new buildings or retrofitted because it's literally just a bit of steel. These are suitable for inelastic deformation, unlike the other ones that I talked about, and it's got long-term reliability and insensitivity to temperature as well. The disadvantages are that obviously it has to be replaced after a disturbance because you're plastically deforming it. It may fracture prematurely due to frequent wind loading. That was pretty interesting. So like if a building was just being hit regularly by a frequent strong wind, it could sort of activate the deformation of these. So they require regular inspection. And the last one is that it's not optimal yet due to its strong nonlinear behavior, but I'm pretty sure there are works going on to do that at the moment. That's all. Thank you.
Hi everyone, my name is Kai Singh and I'll be presenting on behalf of Group 4. My group members are Julian, Renfei Lee and Richard Zhang. And today I'll be giving you 3 examples of building which uses the supplementary damping device. Now before I begin my presentation, I'd like to give an overview of what I'll be presenting today. I'll start off by giving a rough idea of where these buildings are before I go into detail. So we have 2 buildings that we have chosen which are located in California. One is the Arrowhead Regional Medical Center and the Hotel Woodland. Both of these buildings are located near the St. Andreas Fault, which runs for about 1,000 kilometers. And we have our third building which is located in the Philippines. It's the St. Francis Shangri-La Place. It's a high-rise residential area, and it also is located near a fault zone. So I'll jump into the first building, which is the Arrowhead Regional Medical Center. It consists of 6 buildings which are interconnected, and these buildings are 8 kilometers from the St. Andreas Fault. Because of its location, it experiences a site transient or velocity of 1.5 meters per second. Originally, these buildings are designed on base isolation bearings, but the technology at that time, they are not able to meet the deflection requirement for such a site transient movement of 1.5 meter. So they needed something to be implemented into the current design. So what they did was they implemented what was called the viscous damping device. They installed this horizontally, connecting the foundation of the building to either a truss or a column. By installing this, they are able to reduce the displacement requirement of the bearings to only 0.6. Now this device, I have a clear picture here. It's made out of a stainless steel piston, and inside it's a non-combustible silicon fluid. Each of these dampers have the ability or a damping force of 1.4 kilonewtons. One of the main goals when they were coming up with this design is to produce one of the most seismic resistant structure in the world. And this project was completed in June 1998 with a use of 186 viscous dampers. Our second building is called the Hotel Woodland, which is in California. This building is a 4-story building. The ground floor is used for commercial purpose and the others are for residential. It is also worth to note that it is a historical landmark. So when they were coming up with a design to improve its seismic resistance, they had to cater for designs which does not affect its appearances. So again, it's located in an area of high seismicity near the St. Andrews Fault. The largest earthquake to influence the site was of a Richter magnitude scale of 6.75. So what they came up with is a design by using a steel moment frame with the fluid viscous dampers attached on the top. So why did they go with this design? The main reason is at the last point down there. It's because this design, compared to other designs like shear walls, they do not affect the appearance of the building. And secondly, it's easily to retrofit this device into the building without causing any interference to residents who are staying there. But another main reason is because it's able to dissipate large seismic energy into heat, reduce inter-story drift, and it was also a very reliable device because previously this device was used for military application before it's brought into structural application for seismic resistance. And I'll jump into our final example, which is in the Philippines. It consists of 2 towers, and it's a residential building. It's about 210 meters tall. Now, this is located in an area of high winds and seismicity. Its structure consists of 8 outrigger walls, which are connected to the cores. Now, because of lateral movement, this will induce relative vertical movement in the outrigger and the perimeter column, as you can see from the picture over there. And they need to reduce this displacement or any deflection, any vertical deflection between these structures. So they implemented, again, the viscous damper. And you notice all of the examples I have are buildings which use viscous dampers because these dampers are velocity dependent. So the reason why they use these dampers for this building is because it takes less space and it's placed away from the top of the building, which for a high-rise structure, the top of the building will be the most valuable space. And it can also be used over a whole range of amplitudes. So I have a clearer picture of the damping device right there. It's connected, as you can see, to the perimeter column and the outrigger walls. So I'd like to conclude by giving the reasons why these devices are used in the buildings. First of all, it is very reliable given its track record in the military application. It is also cost-effective for some buildings because it can be easily installed and it can be easily retrofitted into. And it takes up less space, but most importantly, it's able to dissipate large amount of seismic energy. And that's the end of my presentation.
Okay, good morning, everyone. I'm Nikish from Group 5, and my group members are Chen Dong and Cheng Bin, somewhere here. Yep. And we'll be presenting to you a type of supplemental damping device called metallic yielding dampers. Alex has gone through a bit of this in his presentation, but yeah, it's not dependent on velocity. I should point that out in the beginning. It's a yielding damper. So, anyways, let's continue. So, why supplemental damping devices? Well, when you're designing a building, you have to sort of compromise stiffness in terms of whether you want acceleration or displacement. If the structure is less stiff, then you'd have higher displacement, therefore it will affect your non-structural components more in an earthquake. Whereas if you make the structure really stiff, then the accelerations will be high, the motions will be very violent, and concentration of forces at structural members. So what the supplemental damping device does is it can reduce both the acceleration and the displacement, and therefore it's sort of a good thing it's a good addition to your building rather. So the idea of using metallic yielding as a supplemental damping device was first introduced by Kelly and Skinner in 1972. And obviously, as the name suggests, it dissipates energy through dissipation, through yielding of a metal, essentially. It is also known as hysteretic dampers because of the nature in which it dampens out the energy. And there are two broad classes of metallic dampers. One is caused by flexural deformation, so through bending, the metal yields through bending, and the other one is through tension and compression. And the metal yields through tension or compression. So the first type of the metallic yielding damper is the U-shaped flexural plate. So the one on the left-hand side is installed between two concrete walls, and the center one is installed between two wooden walls. So essentially what happens is, when the walls rock from side to side, the U-shaped dampers tend to roll, and as it rolls, the parallel legs yield as it forms the U, and therefore it rises up goes up to a certain point, and then under reverse loading it comes back. And obviously, since a certain part has yielded already, the next time when the cycle continues, it goes up and then down, and like that it forms a hysteretic sort of damping behavior. It shows hysteretic damping behavior. Now, an important point is that the yielding is spread over the entire length, so it's spread over the whole thing. So there's the danger of low cycle fatigue is limited because the strain is sort of spread over the entire component. And this is another example of U-shaped dampers. It's an application in base isolation. Here it's placed uniaxially, so it will resist load in this direction. Here biaxially, so it's in all directions. And in this one, the U-shaped damper is placed between your V bracing and the beam, so it's placed there. So those are some of the different applications. Now the second one is added damping and added stiffness, ADAS device. On the diagram on the left shows where it is usually installed. Again, in a inverted V sort of bracing, and then it's installed between the beam and the bracing, similar to what you had here. Now, as you can see from the picture in the middle, when the forces are applied, P and P, it causes the elements in the center to flex, and therefore, due to the bending that is introduced, it causes yielding of the members and therefore dissipates energy. And what's interesting about these members is the cross section. So the cross section is sort of an X-shaped. That's the cross section, and the reason it's X-shaped is to maximize the yielding, so that when it reaches its moment, the moment at which it is supposed to yield, the entire cross section will try and yield simultaneously. And so that's one of the important reasons why they have it as a cross rather than a normal plate. And the last one, so this is the effect of applying the ADAS. So the displacements, the interstory drift, and also the story shears all reduce. So the dashed lines and the other ones after the application of the ADAS damper. So there are significant reductions. And this one, Alex has already introduced. It's your bracing. So it's a buckling restraint bracing. So it's obviously a bracing, and the way they reduce restrain it from buckling is by introducing a steel jacket. So this is your steel core inside, and they have a steel jacket on the outside, and then they have a core. It could be concrete or epoxy or whatever, but then there is a debonding material in the middle. So what that means is it is this member that is in tension or compression, not the whole structure. So what happens is, if under compression, as it is being pushed inwards, the motor in the middle prevents it from buckling. So it's sort of like a continuous restraint through the entire along the length of the brace. And so why the debonding material is important is because it prevents the friction from developing between the motor and the actual steel, and therefore, if the debonding material was not there, the axial forces will be transmitted through the entire section. So the motor will also experience the compression and also the steel jacket, but we don't want that. What we want is it to just act as a restraint. So it pushes, if this is my steel thing, it pushes it in when it's in compression so that it does not buckle out of plane. Again, in this case, the low cycle fatigue is not that much of a concern because the strains are spread on along the entire length of the bracing. Advantages of these dampers, it has a stable hysteritic behavior which is predictable, good for tall buildings because you can retrofit it along the entire length of the building if you want to retrofit. But the good thing about this is if it reduces interstory drift along the entire height of the building. So it's not a concentrated sort of damping device such as base isolation or shear mass dampers which are located at one end. It progressively dampens the energy out. Also, it has long-term reliability. It's just a material you're putting in a structure. It is insensitive to ambient temperature, and we are using ductile steel, something that engineers are already familiar with. And even after it has yielded, it doesn't affect the structural system, the gravity resistance system as much. And the disadvantages are obviously after an earthquake it has yielded, so you need it to be replaced. So you need your procurement system to be there to get this in place before the next aftershock or whenever the next earthquake is. And obviously it's yielding, so it's a non-linear kind of behavior. If you want to know the exact behavior of your building, you would need to conduct non-linear analysis, something which is not very common in practice. And this is just an interesting table that I found from one of the papers. It compares the metallic damper and the behaviors, advantages and disadvantages from the viscous damper that was discussed before and the friction dampers even before that, and sort of compares the nature in which it dissipates energy, really. And that's it. Thank you very much.
Morning, fellow classmates. I'm about to deliver a short presentation on the applications of metallic healing dampers in structures. So our first example is the Izatzaga building in Mexico City, in Mexico. So this structure was built in 1970, before they had any sort of idea of how to provide seismic restrictions to a building. So this building is 12 stories high, reinforced concrete moment frame construction, and a floor area of about 1,200 square metres. So this building experienced moderate structural damage during 2 earthquakes in 1985. Those are the 2 magnitudes there, so that's in standard wave magnitude, which I haven't covered, I don't think. But so due to the high flexibility of the concrete moment frame, this meant that a lot of damage was sustained throughout the building, and also the flexibility of the soil in Mexico City is quite conducive to transmitting a lot of force into the structure. So what they did to repair the damage intermediately was to implement small interior columns. So this was a quick fix type thing, and it didn't really work because in 1986, when another earthquake hit, it got damaged even more, and where there was end fills with brick infills in some of the frames, that began to crack, and so the building wasn't in great shape. So at this stage they decided to do a feasibility study into the introduction of ADAS dampers into the system. So this was done in accordance with the 1987 Mexico City Building Code. So after extensive analysis using time history, using earthquakes that were synthetically made using the standard building codes for Mexico City. They were put in 1990. So on the right there, you've got an image of the west wall, and it shows the arrangement of the dampers within the frames up the height of the building. So in the lower floors, where the force is sometimes larger, there are 2 dampers, and they're placed concentrically on the beam above, whereas in the upper floors, there's just a single damper placed eccentrically in the beam. So there's two pictures there, one of the ADAS damper and one of a damper being deflected and some guy measuring something with the wrong end of the implement. So the result of this implementation was that the interstory drift was reduced by 40% and the fundamental period by 20%. So as you know, by decreasing the period, you actually increase the accelerations in the building, but this was offset by the fact that the stiffness of the building is then increased by the addition of these dampers. So the main issue with implementing a new seismic retrofit for this building was it had to be done without disrupting all the occupants of the building so that they could get along with their lives. So they thought, okay, the ADS is a simple solution which you can just put in with the existing brace system around the building. So what they did was they placed the ADS dampers on the perimeter of the building because this also provides additional torsional restraint as well, which is quite damaging in earthquakes. So the further the ADS damper is placed from the centre of stiffness, the more torsional resistance you get. So that is why they did that. So we're going to stay within the same continent now and going to the USA, looking at the Wallace F. Bennett Federal Building in Salt Lake City. So this one was built in 1960, also previous to a lot of seismic knowledge that we're privy to now. So this is a smaller structure in terms of height, it's only 8 stories. Also a reinforced concrete moment frame, but a larger floor area, 27,000 square metres approximately. So this building is located close to the Wasatch Fault. It hasn't actually been exposed to an earthquake yet, but there is fear that if it was, it would not fare quite well. So they decided to follow the FEMA 273 seismic code for the rehabilitation of the building. So this required them to have a life safety achievement to be achieved. So in the event of a 475-year return period event, that all the lives had to be safe within the building. And then for a 2,475-year event, that the building would not collapse. So similar situation to the last building in that they wanted to design a system that wouldn't incur too much disruption to the occupants of the building so that work could resume as normal. So the solution they decided to employ was a brace frame that encased the original structure. So this was made out of steel, I-beams, I-sections, and I-beams for the columns as well. And then within these frames they placed BRBs, so the buckling restraint braces. So a total of 344 encased the entire structure. And the yield force from these range from 917 to 8,500 kilonewtons. And the lengths also vary too. So there's an image there of the exposed braces whilst construction was going on. So while this was going on, work was still able to continue in the building. So the reason why they chose this system was because the alternative was to provide concentrically braced frames. So as you know, marker Helen. So with a concentrically braced frame, place the elements like that. So you have to have foundation works there, there and there. So in 4 locations for the frame. But with the BRB, what happens is you've only got 2 foundations and it just spans between there like that with connections at the base as shown there. So you've got half the amount of foundation work required, which saves a lot of money. So that saves, in addition also to the amount of steel that's used, because instead of having larger elements for the concentrically braced frame, you've got smaller elements confined with the bracing system there. So overall they saved about $2 million in the retrofit, which was very good for them. And also it saved 2 months construction time because it's a simple bolt-on connection between the frame and the support there, instead of welding to the structure like that. And also it greatly improved the facade of the building, which was a very bland concrete facade. And you've got interesting architectural aspects as well happening there in the main foyer. So this is an inspirational photo of the before and after shot. Hasn't really changed that much apart from the colour and Yeah, it's still a bit of a concrete jungle and monstrosity, but now performs much better seismically. So these are the references. Don't have any recommended readings like Helen has, but you can find them for yourself. Thanks for listening.
Hi, so good morning, everyone. This is Yinglu from Group 7. So my group members are Liu and Shina and Tianyang. So we're talking about the positive damping provided by shape memory outlet today. I just realized nobody has ever given any background information, so I just talk about this briefly. So this low damage building technology is a new technology which has recently just appeared. So it's a bunch of technologies that has been developed like independently from the past few years, but this concept and whole does not appear until very recent. So basically, traditionally, when people talk about the earthquake resistance, we always think about how to build the building to be stronger. We want like larger element. We want a higher grade of concrete, but increase with this building standard, we also increase our cost. So people are thinking from the other end of the bridge, how about we just decrease the damage of the building itself? So here comes our new concept of low damage building technology. This is to restrain the damage level of a building or just to limit it to some secondary elements and a given design seismic grades. So in order to achieve this target, we need to consider more about the flexibility and the ductility of this building, and we also need to focus on something else like level of safety, stringent performance, and economic consideration, of course. So for this damage control system, we often the mechanism of this system is to add or dissipate energy into a structure during an earthquake. Of course, if we want to add energy into the system, it is called an active system, and if we just want to dissipate the energy from the earthquake, it's a passive, and there's also something between them, so combine these two methods together. Base isolation system was developed like 80 years ago. It is one of the most widely used technology of a passive system. So this technology was to isolate the superstructure of a building from the ground so that we could increase the period of the structure, and also we could dissipate the energy because of the deformation of the support itself. The category of such isolation systems, there are mainly two of them. One is elastomeric bearing. So basically, it's just a big piece of rubber. It deforms during the earthquake, so it dissipates the energy. And another one is a sliding bearing, like shown in the second graph. It's like a pile of slices, which could slide between each other during an earthquake, so allows for deformation while the energy is absorbed. And also there's another new kind of sliding bearing, so this one does not have a rubber part in there, it's just like sliding to decrease the friction between these contact surfaces. So the advantage of such a system is very apparent because it's a passive system, so requires no external input of energy, which is quite economical. But because most of them are rubber-based, so this material it could experience aging under pressure, and also when it's exposed to external weather. So it has a very big problem about durability, and also under a major earthquake, it could just damage. So after a major earthquake, we have to replace it. It will be a very big problem because you cannot just remove this whole building to the side and replace the support and then put it back. So to solve that problem, we are going to introduce, this is our focus of today, it's a shape memory outlet material. So it's just basically a metal, but a special metal. It has a superpower of high strain capacity. It could be up to 10% or even 13% without residual deformation. So how could it receive such a huge strain capacity? It's based on its phase transformation property. So it could transfer between this A phase and this M phase. Sorry, I just hate the terminology. The A phase and the M phase under the pressure change or under temperature change. So for traditional material, the deformation is because of the elastic deformation. But for this material, the deformation is because of its changing between two phases. So there's no residual deformation when it goes from one phase to another, and then when it transfers back, everything is back exactly the same. The shape and the state exactly the same. And so this huge strain capacity has brought it with a very big capacity of energy dissipation, which is exactly what we want for our isolation system. So this material, it has a shape memory property, which, if we see from this graph, this is a 3D graph. This extra axis shows the change of temperature. So we can see this curve shows like if the pressure has changed, the shape will just deform in this curve, and if the temperature has changed, so this one shows another way of its shape memory capacity. So if we combine these two technologies together, this is how the new support looks like. So if we ignore these wires, it's just a traditional isolation support. There's nothing else. But these wires we apply to the traditional base isolation systems. It provides external, horizontal, and vertical restraint. If the support is going to deform in either the vertical or horizontal directions, the energy could be absorbed and restored in these wires. So it is often combined with the elastomeric support instead of the sliding support, because they are both depends on like the deformation. And this is an innovative system which we just get rid of the rubber part totally. This is the aluminum disc on the top and the base, and in the middle it's a steel rod, and we have 3 of these SMA rods placed in 30 degrees, so they could have an even distribution of this constraint force. So this one, we don't have to worry about the aging of the rubber material anymore, and also we have a better use of this capacity, deformation capacity of the SMA material. So this one also have very big disadvantages. So the advantages we have already talked about. It is very, it has very high damping capacity. Oh, sorry, it is low intensive damping, and also it has a high energy absorption, and also it has a very big deformation capacity. But the disadvantages is mostly significantly is the cost, because these materials is very expensive in manufacturing, and also this support is costly in installation. So to solve that problem, it is not often used isolatedly. So the shape memory outlet is often used as a supplement to already a working system. Also, another problem is about the temperature sensitivity of this material, because as we talked about before, when the temperature changes, the material will also endure. It will just also endure phase changing. So that is why it is not suitable for countries with very low temperatures around 0 degree. To solve that problems, we can just inducing the current within this material, so we could heat it up to its optimal temperature. But then will also just induce another extra cost of this whole system. also, we just go back to the cost problem again. So, as a conclusion, this SMA material working together with a base isolation system, it has very low intensity damping performance, and it has a very good reentry performance in the earthquake. Also, it is very good in the energy dissipation. The problem of its cost effective is still not as satisfying, and also the application is limited by the temperature of the conditions. We try to figure out some solution for these problems, but not now within our field of knowledge. But we are just looking forward to the future. Maybe with the development in the industry, this material will be produced in like a larger scale, so the cost will just go down automatically. Anyway, it's a very bright there's a very bright future for such materials, and yeah, we believe in that. Okay, thank you for listening.
If you're not using it. It's a good video. It's an awesome video. Okay guys, my name is Craig, and together with my group members Doria, Shinyan and Renee, we're here to present on the passive damping provided by shape memory alloys. Just to start off with, what are shape memory alloys? So they're a class of material, they can recover from large strains through either the application of heat, which is also known as the shape memory effect, or the removal of stress, which is also known as the superelastic effect. They have high damping characteristics, good recentering abilities, and a really good potential for use in seismic resistant design and retrofit applications of buildings. So SMAs, or shape memory alloys, are easily deformed. Once unloaded, there are still residual strains. So if I could just get a pen. If we look at the historic behaviour of the material, usually once it starts off in the austenitic phase of it, and then due to the loading, it undergoes a phase transformation to martensite. And due to the reduction in stress, once it hits a certain stress plateau, this results in this phase transformation back to the original shape. So martensite is formed upon loading beyond a certain stress level, which results in that stress plateau as we saw there. And upon unloading, the martensite becomes unstable, which results in the transformation back to austenite and the recovery of the original undeformed shape. So we primarily looked at some practical examples of these devices. The first that I'd like to present is that of the Basilica of St. Francis of Assisi in Italy. So after a 6.1 Richter magnitude earthquake, which occurred on the 26th of September 1997, there were large cracks which were apparent on what was called a tympanum, which is this structure right here, which is near the roof of the front of the basilica. Rectification work included restoring the tympanum using stones from the original quarry, and also the installation of a connecting device between the roof and the tympanum. Now, this truss was connected using a series of shape memory alloy devices, spaced 50 centimetres apart. So it's actually hidden. So this is the tympanum here, and this is the roof itself. And what was found was what was causing a lot of the damage was the oscillation of the tympanum and roof against each other. So this truss structure was put in using shape memory alloy devices to reduce, I guess, the force transfer. Now, these shape memory alloy devices allowed for example, for a low horizontal force seismic event, this shape memory alloy wires can remain stiff and disallow significant horizontal displacements. For high horizontal force seismic events, the shape memory wires reduce in stiffness to allow for controlled displacement of the masonry walls. And under extremely high horizontal loads, the shape memory alloy stiffness increases to prevent collapse of the structure. And over here we've got two different types of hysteretic loops. And the reason for this was the different, through finite element analysis, I think what the designers saw was there was a different stress distribution across the tympanum, and this resulted in the use of different length of wires, which would require different behaviour at different points. So the second example that I'd like to go through is the San Giorgio church in Italy as well. So after a 4.8 Richter magnitude earthquake, which occurred on the 15th of October 1996, investigations showed the propagation of significant transverse and through cracks in the masonry infant walls. I'm not sure if that's very clear, but there were large cracks that formed. So the rehabilitation of the bell tower consisted of the installation of 4 vertical pre-stressing steel tie bars with shape memory alloy devices. So over here in each corner of the building, that's a side-on view. So it consisted of the placing of these 4 vertical pre-stressing bars in the internal corners, and they were anchored at the top and the bottom. And so the goal of this was to really limit the force applied to the masonry by post-tensioning the shape memory devices, which allowed the masonry walls to constantly be in compression. Finite element modelling analysis was used to determine the amount of pre-stressing. Over here we've got the acceleration time history in both the north-south and the east-west direction. It was found that the east-west direction was more critical, and that acceleration was used in the finite element modelling. And as you can see here, the blue, areas of this model show a high stress distribution. And from that, the amount of pre-stressing was gained. So these SMA devices were tested with a 4.5 Richter magnitude earthquake, which actually occurred on the 18th of June 2000. An investigation showed that absolutely no damage occurred to the tower. So in conclusion, we found that shape memory alloys are capable of providing constant forces and the ability to, dissipate a lot of those strains and return, their sort of strain back to the original form. They're particularly useful in the presence of crack propagation, creep deformations, or settlement phenomena. And these features, together with their limited encumbrance, make shape memory alloy devices particularly suitable for passive damping and retrofit of cultural heritage buildings. I've got a quick demonstration of use of the shape memory alloy wires that I'd like to show you. So what's happening here is he's lowering the temperature of the actual wire, and then he's going to heat it up just to show the transformation from a position of maximum strain to the original strain.
I can drop it below its transition temperature. Now in its low temperature phase, I can deform it like I did it before. And I can now take it out again, but this time I'm going to try and heat it up quickly, because before it took a while to heat up. So obviously there's a lot of energy stored in there, because I put a lot of energy to deform the material into its new phase. So here we go. I'm going to drop it in. I'm going to stand a wee bit back because it's going to go like crazy. Whoa! There we have it. Didn't quite go according to plan, but never mind. It illustrates the point. There we go. I'll do it again just for the fun of it. You can see I can have endless hours of fun with this. Here we go. 1, 2, 3. Whoa!
There you go. So the application of heat.
You've got it. Look at that. Fully transformed back again. And of course, that's to be expected because it's not
reduction of the residual strains. Thank you.
Hi guys, I'm from Group 9. Just before I start the presentation, I'll indicate that I've made things pretty basic rather than going into detail and putting you all to sleep. A few good concepts from this tie in really well with what we've done in Earthquake, so I thought it'd be pretty good to go over those. I've just got a bunch of dot points which, rather than reading them out, I'm going to go through with our picture. So basically what we have is a rocking post-tension precast concrete wall system. And so what that is here you can see the walls, and in these walls, these precast walls, we've basically got ducts. And in these ducts, as you can see, we've got strands. And now these strands can be stretched a long way. And so what you do is you anchor the strands at this foundation and anchor them at the other end with a live anchorage at the top of the wall. So basically what you have is a wall with almost like an elastic band in the middle. Now an important thing to understand is that these strands aren't actually bonded to the inside of the duct. So it's almost like it's a pipe and then the strand goes inside this pipe, if you can visualize that. And so this is just another diagram showing you how the whole system works. It basically rocks because of this strand, and I'll go into more detail shortly. Another diagram where you can see this precast wall with the duct and the tendon inside anchored at this foundation. Okay, so basically what happens is the building and system is constructed in such a way that extensible connections can form under earthquake loading, and as a result, rocking can ensue. During an earthquake, the building is subject to ground accelerations, which results in obviously the building trying to displace. When the walls displace, these strands that are inside these ducts can tension up. And what happens is that at every level, these strands, and in the beams as well, you get this clamping effect where the strands pull the structure back towards the foundation. And you'll see this illustrated in a video where basically he explains what I did, but I don't want to waste time. Please do.
So this is the joint between the building up here and the ground. So this steel box is on the ground, and this main column, along this joint here, it can rock on the steel box when we have an earthquake. There's a large cable that runs right through the middle of this column and is buried down in the basement. What that means is as the column pulls over, it will then try and straighten the building up so that it always comes back to upright, which is important for people coming in and using the building straight after the earthquake. So these are the removable dissipators. If there's a large earthquake and they want to be replaced because of the amount of work they've done, you can unbolt these, take them off, put a new one on. Building's as good as new. We did about 4 iterations of this joint to get it looking nice and getting it real simple to build. We went through quite a rigorous procurement process and testing different options in terms of finding the easiest way to assemble it and what the cost benefits were for the external energy dissipation for the client. So really I think the building's turned out very well for everyone.
Basically in this system what you can see is these are the various walls and they're connected by these shear connectors which then essentially undergo some kind of plastic deformation, and so the system can move as a whole together and move in unison. I guess a key thing to point out, I'll show you this video as well. Not going to work. This is just a video to show basically how one of these walls actually works together. Not very exciting. No trucks falling like Alex's, unfortunately. Okay, so you're probably wondering, why is this rocking advantageous? Well, basically the rocking mechanism allows the structural damage to be effectively distributed when experiencing an earthquake. Since the precast elements constitute much of the structure, there are dry connections. You're not really just pouring a slab and a column together, they're just connected by these strands, really. Basically, as a result of these dry connections with precast elements on top of one another, what it allows is for you to basically design where you want your plastic hinges to occur. Because these aren't rigid connections or wet connections, you can have these plastic hinges forming all over the system. And as we've discussed with Helen throughout the semester, what we want really is a beam sidesway mechanism where rather than getting a soft story occurring where perhaps all the moments and the rotation is about one place, because all these are precast elements that aren't connected with wet connections, basically what you can get is hinges forming at all of these. So rather the entire rotation just be taking up one floor, the energy dissipated is throughout the whole system, and so the rotations at each hinge would be less than if it was just at one or a few. And so now quickly on to the advantages. Significantly reduced damage to the structure itself. Obviously, because the system gets pulled back, it recenters, and this is highly advantageous because if you have an earthquake and your system's displaced, then what do you do from there? It's a bit of a debacle. The unbonded post-tension tendons have shown reductions in residual displacement, so the actual displacement of the building itself is reduced. Localized inelastic strain is avoided as the tendons are not bonded to the shear walls. Now this is more of a construction benefit because you're using prefabricated concrete, modules. Less time and labour is required on site to actually procure the materials, and the materials are immediately available for use. So unlike when you pour a concrete slab, you've got to wait 7 days or 28 days for a certain amount of strength to exist within that material, you can just use it straight away because it's ready at strength. And the modular elements make the assembly straightforward because basically it's like building a more complicated Lego. The initial force in the tendons must be selected carefully to ensure that they don't yield at large drift ratios. Since there is anchoring of the tendons to the foundation, it is near impossible to gain access to them, need they be replaced. So obviously if you've got the tendon going all the way into their foundation and it's anchored, actually accessing that is very difficult. The system is not common yet, and so the contractor undertaking the works will more than likely be unfamiliar with it. Pretty straightforward. So even though historically it's easy to build, people are still unfamiliar with it, so they're still learning on their feet when they're using this system. And also long-term durability is a concern for the unbonded tendons. they're my references, and Helen looks happy, but I'm a bit worried that not so much. Thanks, guys.
Where is it? Which one? Where's it all? Which folder is it in? Sorry? Desktop, is it?
Try the documents.
Document. CVEN90017. The presentation.
Hello, my name's Jared and I'm representing Group 10. I'll take you through some practical real-life examples of rocking post-tension precast concrete wall mechanisms. Rocking's been built in structures occasionally since ancient Greece, but the focus on seismic design for damage control became popular in the 1990s. And precast seismic structural systems, or press systems, are a key part of this. They involve post-tensioning the steel tendons that yield at rigid connections to allow lateral rocking, as has been previously mentioned, and this requires anchorage or clamping of the post-tension strands to the frames and walls. This figure down here shows you how the self-centering of the post-tensioning combined with this energy dissipation gives you this flag-shaped hysteretic hybrid system, which is what we're after. Two recent buildings that have been built with this construction technique are the Allen Diamond Building in Wellington, New Zealand, and the Paramount Building in San Francisco, USA. Those are those two there. They were built and designed successfully, but neither of them have been subjected to earthquake loads yet. Two that have are the pressed 5-storey precast test building built by the University of California and the Southern Cross Hospital in Christchurch, which was subjected to the two well-documented Christchurch earthquakes. First, we'll look at the University of California test building. After 10 years of research on precast seismic structural systems, they built this here 5-storey concrete precast building. It was designed at a 60% scale and was subjected to 50% higher loads than is stipulated in the Seismic Region 4 of the Uniform Building Code. It was designed using the displacement-based design method, which aims to reduce maximum drift to less than this 2%. The frame under study was the hybrid frame mentioned earlier. It relies on unbonded post-tension steel tendons, and this is a diagram down here. This is the major, was built with major post-tensioning down through the central beams, through the column joint, as well as mild non-precessed steel closer to the beam interfaces. And that's what creates, combining those creates that flag-shaped hysteretic behaviour that we spoke about earlier. Under these simulated loads, minimum damage was observed, which is good. This pre-stressed system dissipated less energy than a non-pre-stressed system would, but the maximum drift was much less. Drift is a vital parameter in earthquake design, of course, and this is a major factor in pre-stressed post-tension precast concrete wall mechanisms. One drawback was that the floor forces were higher than expected. Floors that act as diaphragms tend to tear in jointed wall systems. However, this is a problem in non-press systems as well. The Southern Cross Hospital in Christchurch was the second precast press building in New Zealand. It was a precast unbonded post-tensioned frames and had coupled walls in both the north-south and the east-west directions. It was coupled by U-shaped flexural plate dissipators. These dissipate the rocking mechanisms, and this combined with the post-tension self-centering of the steel of the unbonded tendons. This is down here is a picture of one of the U-shaped flexible dissipators that we used to dissipate the energy, and this is what the final building looked like. No damage from the 4th September 2010 7.1 magnitude Darfield earthquake was noted, and only minor damage from the 22nd of February 6.8 magnitude Christchurch earthquake was found. The Christchurch earthquake was much closer. Minor crushing was found on the concrete couple wall interfaces down on the south wall on the side. And analysing the U-shaped dissipators revealed that the interstory drift was between 0.5 and 0.75%, which is adequate. Allowing this rocking alleviated the need for the development of plastic hinges in the concrete, and this reduced the structural damage to the building greatly. The self-centering vastly reduced the residual lean after the earthquake, and this increased the operational capacity of the building. Many important facilities within the hospital were operational the very next day. Damage control is an important part of our building design these days, and this press system was touted as one of the best and construction techniques that they will use in the future in Christchurch. Thanks for your attention.
So hello everyone, I'm Jianan, and I on behalf of Group 11 to give you this presentation about tongue twister, which is the post-tension and bonded tendons in precast concrete frame. It's too mouthful. So first I will give you a brief introduction about what is PT tendon. So in this picture we can see that this is a column and this is beam, and during the construction, we buried the tendons inside the beam, and with some certain length along the tendons, we make it unbonded from the concrete by using some cover or case or tube to avoid the concrete getting bonded with it. And in application cases, people always do like this. So if using this picture is too abstract, so just take it easy, forget it, because in the following part I will introduce you two basic applications in the concrete frame about this technology, and I hope everyone could have a much better understanding after I finish my presentation. And the first one is a hybrid frame, which is it combines the PT tendon with rebars, and they work together. And the second one is with the frame only got the PT tendon to resist the earthquake actions. So for the hybrid frame, this is the elevation view for a typical hybrid frame. So we can see the green lines is the PT tendon, which is unbonded from the concrete. And the orange lines, they are the rebar located at the upper level and the bottom level of the beam cross-section, and they work together. And we also use two PT anchorage at the two ends to restrain the tendon. And if we take a closer look and for the joint, we can see that here is unbonded PT tendon is here, and in a further location from the joint, the rebar is bonded. But in the location which is very close to the joint, it is locally unbonded. And for the interface of the column and the beam, we use concrete or fiber to fill it. So when the earthquake occurs, the joint deformation could be like this, and the tendon works, and also there exists a very high compression in here in the concrete part. So these two things prevent the steel from yielding, so all the structural elements remains in elastic stage. So when the earthquake is over, it goes back like this. And if the earthquake back action from the other directions is like this, and when it's over, it's go back again. So So from these things, we can find that there is the most important advantage for this design is compared to other structures. Is in this design there is no residual displacement after the earthquake occurs. So it enhances the building strength after the earthquake occurs, and there will be no stiffness loss or the strength loss, which can be potential risks to damage the whole building. And for the PT only frame, it's pretty easy, and it's only got the PT tendon inside without any rebars, and its joint is like this, and because it's got no rebar inside, so its joint is too rigid. Yeah, and its deformation, yeah, like this. Yeah, but quite similar, but not flexural and ductility as the previous one. So, and I also did the mechanism analysis. So here, as I just mentioned, the parts in here, the concrete is in compression. So during the design, we need to pay extra attention on the concrete strength, and we need to take some measures to increase the concrete strength, like using the confinement or just increase the concrete grade. And I also did some comparisons between the PT joint and the rebar joint. So for the PT joint, it's always returned to the vertical location, and it behaves non-linear elastically, and it's got low damping ratio since it's too rigid. And for the rebar joint, it's always have some remaining displacement after the earthquake, and it behaves non-linear elastically, and it's also has a very high damping ratio, so which means its energy dissipation is much larger than the PT joint. So for the advantages is obviously we can see that there's no or little residual displacement for this building reinforced with the PT tendons, and the PT tendons could protect the beam and the column by transferring the deformation to the joint, because the joint takes most of the earthquake actions, and since the whole structure is precasted, so it simplifies the design process and saves the construction time. And it also has some disadvantages because the joint is rigid and it causes the force or the stress concentration. So we need to pay extra attention to the concrete crush or the shear reinforcement, and it's got little energy dissipation without the help from the rebars. So therefore, our group suggests that we supposed to use a hybrid frame in the real case in the future. So thank you.
All right, so thanks for that. So yeah, our group 12, it's got myself, we've got Daniel, and we've got Wei Ping, best group in the class, I reckon. Don't you agree, Helen? So pretty much we're looking at the precast concrete frames as well, with the focus on frames rather than walls, like what group 10 had, I think it was. So we're looking at two structures in a little bit of detail. The first one is the Alan Diamond building, which was part of one of the universities up over there in Wellington. And the second building is the endoscopy building in the Southern Cross Hospital in Christchurch. So to assess these buildings, we're using the criteria that came out of the Christchurch Royal Commissions, which of course is the affordability, durability, ability to self-center, non-structural damage, damage mitigation, and repairability. So firstly, we're going to look at the affordability. So of course, the university building at the Alan McDiarmid, $40 million for 6,000 square meters, while the second structure, the Southern Cross Hospital building, was $7.2 million for only about half the square area. where, of course, the university building, that price includes the research facilities, so it's expected to be much more expensive, and it's in fact estimated that the actual structure itself was about the same as it would have cost if it was a regular reinforced concrete structure. And pretty much the reason why that this structural system is so cheap is because it is a precast system. You have, a little bit of cost added due to the seismic structural system, but also the cost savings due to the precast, so you save a lot more time in construction. So that, of course, is a huge tick for affordability. Now, going on to durability, because this is an internal structural system, overall it actually works out pretty well. Some of the other ones, you've got parts yielding, things can go wrong. Where with this, as long as you protect it from moisture, it's mainly okay. As you can see here, there is a bit of rust and decay building up on this, but of course that's much easier to fix than yielded parts. Where in this one you can see that they've got a bit of plastic adhesive covering this edge to really try and keep the moisture out. Yeah, and one of the other issues is that you do need to make sure that the gaps are not filled over the building's lifespan, because of course, in 10 or 20 years, a tradesman might come along, see this gap in a beam, and think that it's not safe and fill it in. But of course, the gap is really meant to be there to allow this part to rock, to allow the beam and the column to bend together, because we don't want that to be a bonded connection. We don't want that to be a rigid connection, I should say. So of course, durability, as long as you take care of it, that's another tick. Now, the ability to self-center, as was already covered by the previous groups, the post-tensioning, pretty much, the way to imagine it is it really pulls the structure back in, because, I guess the least position with the least energy stored in the post-tensioning is just the vertical position. So, of course, the structure, it might go up, it might deform a bit, but then it'll get pulled back down. Then, of course, when you combine that with the hysteretic loop, you have the really nice flag-shaped hysteretic damping system. So that's another huge tick for the ability to self-center. Now, coming on to the non-structural damage. So the hospital building, as was already said by Group 10, it did go through the Christchurch earthquake, and especially the big aftershock, the magnitude 6.3, that was only 10 kilometers away from the CBD. Now, kind of luckily for us, the structure was only completed a couple of months before the earthquake, so it's really the perfect example to illustrate how the structural system actually works in an earthquake. So the first thing is we've got to assess the damage of the structure. Now, because it's a hospital building, a huge issue is the damage that goes on both inside and outside. And of course, there's a lot of sensitive equipment, and the fact that the hospital was able to open just the day after the earthquake really shows that there was no non-structural damage. And to look at the structural damage really shows to look at the Christchurch CBD. So as you see here, and you zoom into a bit more detail here, there's a few buildings still standing, but there's a lot of empty sites in the CBD where buildings have simply been demolished. And then coming up here, which is where the hospital is located here, you can see that there have been some larger buildings that have been destroyed, but the actual endoscopy building is actually fine. So just tick to that. Now, damage mitigation. As was previously said, there was a little bit of damage at the interface here between the column and the beam, and that's mainly because there's that rocks back and forth. There's a little bit of spalling, a little bit of cracking. Now, they've tried to really prevent this damage by having the steel armoring there, but as you've seen, it hasn't worked 100% of the time. So what some researchers are currently doing is looking at reinforced fiber polymers in concrete just to really strengthen up the end zones of the concrete there. So when you have the pounding force, rather than it being brittle and cracking, it's really got something to tie the concrete together a little bit better. So as long as you design for that, damage mitigation, not really a problem. Now, repairability. Obviously it is much easier to repair this cracking and spalling rather than a plastic hinge as you would have in a regular reinforced concrete structure. So both cracking and swelling, that's fine. So we do have one problem, which of course with the post-tensioned cable inside of that, it's pretty difficult to replace post-tensioned cables, so that's not really a good thing. But of course it is much easier to replace a post-tensioned cable than it is to actually replace the reinforcement in a concrete beam. So overall, it's a pretty big tick for repairability. So in summary, we've gone through the affordability, that's fine, durability is good, ability to self-center, non-structural damage, damage mitigation, and repairability. So overall, if you're looking for a structural system, mainly this one is for low-rise structures, I should say. Low-rise and of course, structures that you are willing to invest a bit more money in. but overall, yeah, it's a great structural system. So thanks for listening.
Hi, so I'm from group 13, and we're going to talk about the base isolation system. So what is base isolation system? It is a flexible system that is installed at the base of the building, and it will isolate the building from the ground movement. And this will also decouple the building from the ground movement as the effect of the earthquake. This system will also absorb most of the seismic energy that is imposed on the structure. So how it works is, on my left-hand side is a normal, non-isolated building, which is rigidly connected to the ground. And in the middle is like more a theoretical, perfectly isolated building, which sits on top of roller supports. So when the earthquake strikes, the building itself will move along with its foundations, so there will be no local displacement occurs on the building. But in reality, we cannot have this, so what we have is the base isolation systems, and what it will do is takes most of the displacement, and the rest of the displacement will be transferred to the building, which is very, very small. And this is just a picture of the base isolation, which sits on top of a column at the foundation. So how it really works is the base isolation introduced phenomenon, not a phenomenon, but it's introduced a period shift. So what it really does is increasing the period of the whole structure. So we have these two graphs of the RSA and RSD. So when you increase your period, your acceleration will decrease, but the displacement will increase. As this sounds, most of the displacement will be taken up by the isolators, so the displacement of the building itself is really small. And the base isolation system also includes some damping mechanisms. So compared to normal non-isolated building, which is usually assumed to have 5% damping, isolated building will have 25% damping. This is just the types of normal base isolations, which is one is the elastomeric bearings, which is a steel or lead encased with rubber. And the other one is the friction pendulum bearing, and the friction pendulum bearing usually have larger displacement capacity up to 1 meter. So what is the advantage of the base isolation? It reduces the damage and enhances the structural integrity of the structure. Usually in general, there's no maintenance required throughout the building life, but when a great earthquake occurs, usually you have to have it replaced or maintained. And this base isolation also allow some buildings of high importance to continue to operate. This is especially really important for buildings such as hospitals and government buildings. It is possible to use this system as a retrofit, to retrofit existing buildings. And the cost-wise, it only adds up to 3% extra to total construction costs. The disadvantage of the base isolation is it's not work for all types of structure and all types of sites, as soft soil and tall buildings usually have higher and higher natural period. So where the effect of the period shift is not really effective, as if you can see, if let's say your period is around 2 seconds and you're going to introduce the period shift, the reduce in acceleration is not that much, and your displacement will be capped at that. In this case, it's like 0.5, and it will be not very effective at all. And there will be some construction challenges in terms of the surfaces. I can see from these pictures, this is from a project in Chile, and what the contractor did, I think they over-designed the concrete where the isolators are supposed to sit on top of it. So there's a lot of stir-ups, and they cannot put the connection through the concrete. So they have a lot of more work to do. So they have to remove some of the stir-ups and put some tubes to let the bolt to go through. And because the isolators are very flexible, it usually comes at the expense of the required rigidity under small and frequent lateral loads such as wind and traffic vibrations. This is just the references that I use for the presentation and the report, and that's all.
Thank you very much, everyone.
I'm going to do it next week, don't worry.
Yeah, you sort of get all revved up to do it. So, but I just